wanted to work through an example that involves a Michelson interferometer and the interference pattern of a Michelson interferometer. If you recall, the interference pattern comes from splitting light into two paths, then recombining the light from the two paths, and the constructive destructive interference of the light from the two paths creates a pattern of bright fringes, dark fringes in the Michelson interferometer. You can use the interferometer to measure wavelengths. You can use the interferometer to measure distances. You can also use the interferometer to measure refractive indices. And this example involves measuring refractive indices. So in this example, added to the Michelson interferometer is a cell, a glass cell. And that's pictured here in this sketch. And this cell initially is empty, it has vacuum in it. And then this cell is filled with a gas. And we're going to figure the refractive index of the gas based on the change in the pattern of fringes that occurs when you replace the vacuum with the gas. The fringe shift is due to the following facts. So in vacuum, there's a certain number of wavelengths inside the gas cell as the light travels firstly from the left to the right and then back through the cell from the right to the left. When the cell is filled with gas, there's a different number of wavelengths in the cell when the light travels firstly towards the mirror through the cell and then back away from the mirror through the cell. And there's a different number of wavelengths when there's vacuum in the cell compared to when there's gas in the cell, because the wavelength of light is changed in a medium by a factor that's the refractive index of the medium. So if lambda is the wavelength of light in vacuum, then lambda over n, the refractive index, is the wavelength of the light in the gas. And so the wavelength of the light is a little longer in the vacuum. The wavelength of the light is a little shorter in the gas. And so there's actually more wavelengths that fit in the cell when you've got gas in the cell, less wavelengths that fit in the cell when you've got vacuum in the cell. And so you get a corresponding change in the fringe pattern. You get a fringe shift. So let's go ahead and solve this problem. I'm just going to start by sort of summarizing some of the numbers, some of the facts that were given in the question. The question says a Michelson interferometer has a 5 centimeter long gas cell in one arm. It's over here on the right. We're told that there's a fringe shift of 160 fringes of 600 nanometer light when the contents of the cell are changed from vacuum to gas. And based on that information, we've got to find the refractive index, lowercase n, of the gas. So let me just write down the numbers that are relevant here. We've got wavelength of light is 600 nanometers. We've got length of the cell, that's 5 centimeters. And we've got the number of fringe shifts when we fill the cell with gas. That's 160. That means that we watch the fringe pattern, we see a location on the fringe pattern go from dark to bright to dark to bright to dark to bright 160 times. There's 160 fringe shifts. So the first thing I'm going to write down is the number of wavelengths of light there are across the tube, say when the light travels towards the mirror or away from the mirror. So across the tube, in these two cases of when there's vacuum in the tube, when there's gas in the tube. So number of wavelengths in tube for vacuum. Let's take that case. How many wavelengths are there across the tube when you've got vacuum in the tube? Well, to figure that out, all we've got to do is take the length of the tube, that's L, it was five centimeters, and divide it by the length of one wavelength of light. And that's just a number. We've got dimensions of length in the numerator and denominator, and it's just the number of wavelengths of light that stretch across the tube when we got vacuum in the tube. We can write down the same thing when we got gas in the tube. Number of wavelengths in tube for gas. Now this again is the length of the tube divided by the wavelength of the light in the gas. And the wavelength of light in the gas, as we noted over here on the sketch, is shorter than the wavelength of light in vacuum by this factor that's the refractive index. So this number of wavelengths will be L divided by lambda, which is divided by N. And so this is the number of wavelengths when we got gas in the tube. The first line was the number of wavelengths when we got vacuum in the tube. And they're a little different. They're a little different by a factor of the refractive index. There's a little more wavelengths when we got gas in because the wavelength is shorter. There's a little less wavelengths when we got vacuum in there because the wavelength is longer. Now, what we see in the experiment, what we see in the measurement is a fringe shift. And we see that fringe shift because there's a number of wavelengths in the left-right arm of the Michelson interferometer. There's a number of wavelengths change in that left-right arm when we replace the vacuum with gas. So what we're really interested in is the difference between these two number of wavelengths. And so let's write that down. So this is the change in wavelengths. When we go from vacuum to gas in the tube, and it's just going to be the L divided by a lambda over N less the L divided by lambda. That's going to be the change. Now, the two terms with the gas and with the vacuum have a common factor. So it'll be more straightforward if I pull that common factor out. That common factor is L over lambda. And then secondly, this N in the denominator of the denominator, I can move up to the numerator. And so I can write this difference in the number of wavelengths as L over lambda, that was the common factor, times N minus 1, the difference of the refractive index of the gas from 1, which is the refractive index of vacuum. Now, this is the change in number of wavelengths. The change in the number of fringes is 4 times this change in the number of wavelengths. That's because if you add 1 wavelength to this region of the cell, well, firstly, the light travels at extra wavelength when it goes to the left and when it goes to the right. So it's really adding 2 wavelengths. And then secondly, when you count fringe shifts, you're counting the change from bright to dark. That's half a wavelength. Then dark to bright, that's another half wavelength. And so there's a factor of 4 difference between the number of wavelengths change when you traverse the tube and the fringe shift change due to the light traversing the gas in the tube. So change in fringes when we replace the vacuum by the gas is going to be 4 times L over lambda times the factor n minus 1. And this change in the fringes, this is a number we know. This is the 160 fringe shifts that we were told in the question. So finally, let me write this out as a sort of summary formula of all our arguments that we put together here, that the fringe shift that we observe is 4 times the length of the gas cell divided by the wavelength of the light times n minus 1, the refractive index minus 1. Now, of course, we're interested in figuring the refractive index. So let's rearrange this equation by multiplying through by lambda and dividing by 4L. The fringe shift times lambda, the wavelength, divided by 4L is equal to n minus 1, the refractive index less 1. And we can plug in all these numbers on the right-hand side now. So 160 was the fringe shift. The wavelength is 600 nanometers. That's 0.6 microns. I'm going to work in microns here for convenience. In the denominator, we've got a factor 4. And then we've got the length of the cell. It's 5 centimeters. That's 50,000 microns. And I've already worked out what this ratio is. I got a value that is 0.00048. And so that's the difference of the refractive index from 1. And so finally, the refractive index itself of this gas is 1.00048. It's a little higher than the refractive index of air. That's 1.00027. Anyway, there's an example of the Michelson interferometer. It's an example of the interference patterns in the Michelson interferometer. And it's an example that you can use the Michelson interferometer for a lot of practical purposes. You can use it to measure wavelengths. That's one example. You can use it to measure distances. Second example. Here we used it to measure a refractive index by comparing or measuring the fringe shift with and without the gas that we were trying to measure the refractive index of.